All right, folks, welcome back. I think we lost a few people. I'll take that into advisement in how we're doing this. Um, so I have just 4 more slides that I had pre-prepared for you about model selection. We'll go over that, and then I'll turn it over to Mark. So in many ways, the leave one out cross-validation with the implementation of mean absolute percent error or root mean squared error, all those various metrics you can get, is a way of identifying a best model. But those are methods for identifying a best model using out of sample predictive performance, which again, I think has a lot of merit, because this is exactly like the situation of forecasting, right? You're not going to use the incoming number of fish in your forecast model. You have to predict it before it happens, obviously. So there's a nice properties that those leave one out cross-validation techniques have relative to the thing we're actually trying to forecast. But I would be remiss if I didn't also talk about good old-fashioned Aka-Ike information criterion type ideas and how to do model averaging. So what I have here is this horrendous, yes?
Before you leave one out cross-validation,
yeah.
can I ask a question about it?
Okay.
Especially in relation to forecasting. You mentioned before, like, in some ways, if you leave out a year in the middle, that's really an evaluation of how your forecast is in terms of you're using sort of data from the future to predict that year, which is not generally what we're faced with. So at the same time, if you only use the time leading up to that year, it's more realistic in terms of what the model would have done if that was used that year. But you're then maybe biasing something like, well, use 20 years of data, probably doing better than if you only use 10. What other trade-offs or thoughts you have about, like, how does that feed into what?
Yeah. Well, I guess I want to just reemphasize that I am fully aware that this doesn't work well when you have time series type analyses, and breaking the data set apart like that creates a number of issues. As to the second part about future data not being useful, I still think that there's value there in the sense that we're trying to figure out if X is related to Y. And the time at which it happens doesn't really matter. And to the extent that maybe it does matter, that past conditions are no longer occurring today, right? This is non-stationarity, which I think we can circle back to later on. That is also a really important consideration. So it's quite possible that what happened a long time ago is really not useful for predicting what's happening now, right? And if that's the case, then maybe you shouldn't even be looking at a long time series, right? You should maybe just chop it off at a certain point, and we can come back to that issue. I don't know. Do you want to elaborate? Because I think there was more to your question, but yeah.
Cohort base, so
you know what you had last year.
In reality, if you know what you have next year and you're trying to use that to predict what you have this year, like, that's not a situation we actually have access to. So that's
right.
So does it make sense to throw that into a kind of leave one out? Like, where you're just leaving 1 year out, so does it make more sense to evaluate predictions each year, but using only data up to that year?
Right. Yeah, so I think a lot of people in this situation do what Mark had already kind of alluded to, which is where you're only forecasting the leading edge, right? So so you can maybe only have a leave one out cross validation for the last 4 or 5 years, right? So you're using all your historical data to estimate 2001, 2002, 3, 4, and then you're just done. And then, yeah, so you're really only evaluating the performance, not on the full data set, but on the most contemporary parts of it. And I was going to show you an example of that. I don't know if I'm going to find it, but this is, I think, a way of addressing that. I don't know. You can go ahead and tune in on or chime in on that while I look for something I can maybe use to help illustrate.
That's typically the way to fit model up to some point and then start evaluating forecasts and just do later which usually involves a refitting. Forecast next year, we observe next year, then we refit, right, forecast T+2.
So is there a minimum chunk of data you'd want to have before you can start making those predictions? Like you don't want to go predict year number 2 based on your time series one data point, probably, or it's not as helpful.
Unanswerable question. I mean, this comes up all the time, especially in times of great.
How much data do I need? All of it.
Yeah, and more. Yeah, so sometimes I usually depend on the system, what's the ratio of process type. So, yeah, and and then the other thing would be to consider, when you want to evaluate that skill at the end, how many values do you need to calculate the squared error or something like that, especially if you're going to compare multiple models in order to have a meaningful comparison. Okay. I mean, you probably accomplish this in some amount of simulation, but then
Well, here I can tee off on this a little bit too. This is real work with coastal Fall Chinook in Oregon. And I did this a long time ago. So the series ends at 2015. But here I'm using cross-validation to assess the predicted performance only in the final 4 years. And so now obviously we have more data. This is a long time ago that I did this. And then the different rows here are, I think it's like 12 different populations. And then the number that's in here is the mean absolute percent error. Okay, so I'm really only calculating this for the end. And the reason why is that this whole brick of columns, this is for one type of model. This is a neural network model. And then this is another different kind of neural network model with different covariates in it. Here's a sibling regression. Okay, and so I can't really apply the leave one out cross-validation across every year because the models don't work when I break the data set apart. So I'm really just using the beginning up to the focal year, 2012, 13, 14, 15 for the prediction. And then this is maybe of interest. So this is the absolute percent error in the numbers here. I know you maybe can't see. I can zoom in, I think. Yeah, zoom in down here. So we're looking at the absolute percent error for all the populations and 4 years. And then I just take the mean of it right here. So this is the mean absolute percent error, 0.64. It means that they're about 64% off. That's not good. Okay, and this is with a fancy neural network model. Okay, now to further illustrate how bad this model is, let's just compare it to the naive model that Mark had spoken of, where what I've done here is I've just taken the average of all the abundances, the thing I'm forecasting, and use that to make a prediction. And then I'm going to color code when I get closer to the truth with the naive forecast versus the neural network. Okay, and so if it comes out red, that means that the naive forecast actually did better than the neural network model. And so we've got the same years here, right? It's the 2012, I got it right here, 2012, 13, and 14, 15, all the populations. So this means in 2012, just using the average worked better than using the neural network model, right? And for 2013, that happened in these first 3 populations. So the more green you see means that the actual model outperformed the naive model. But this is really bad, right? Because look at all the red on there. And I've got a number of models here, and so I'm going to scroll to the side, and you just like visually just want to look for the ratio of green to red. Right? This is just a really simple way of assessing how bad these models are. And they're quite bad. We start getting like a little bit okay here, right? This is a decent one. But the mean absolute percent error is still 60%, but it works a little bit better than just the historical mean. But these are a lot of kind of bad models. I'm going to return to this theme a couple times here before I relinquish the podium. So some of the best models were just these simple time series models, very simple time series models, and sibling regressions were generally the best. But this is me just like, trying to figure out which models are working best, which techniques, which covariates. There's different features of the models, like how many time lags, and the neural networks have a number of bells and whistles you can play around with. So anyway, your point is taken, Kevin, that you can't do the leave one out cross-validation the way I've described it for all kinds of models, right? In many cases, you're just gonna, and it makes good sense to really only do it on the end. But that's up for you to decide if you can or cannot do leave one out cross-validation on all your points, or if you just want to focus on the terminal part of your data set. Okay, so a lot of text here, but I put it in the slide mostly so that you'll have access to this later. This is an excerpt from Burnham and Anderson's textbook on multi-model inference in ecology, or I forget what the subtitle is. But it's a foundational fundamental text. I think it really actually changed the way we do science more than many other texts ever have. I should say science within ecology, and not science more largely, but these are two ecologists. Well, they're statisticians, but their applications are in ecology. And it's a very advanced textbook. If you haven't seen it, it's a lot. But here's just some pure English. So not likely to open this book and just find a page of English. But anyway, I'm just going to read what I have highlighted here. And then if this kicks off some interest, I would encourage you to read the rest of what I've put in the slide and maybe even check the book out someplace. But here's what they say. And these are really leaders in the field 22 years ago. We are led to believe that the only legitimate application of all subset model fitting, so this is, you've got a bunch of models with a number of potential covariates, and you're gonna like look at all possible subsets of all the different covariates that you can throw at it, including the quadratics and interactions and all that. So the only legitimate application of all subset model fitting with purely observational data, which is always what we're gonna have, is prediction. Well, we're doing prediction. That's what forecasting is all about. So this is a little bit of a warning of like, hey, don't look at all subset modeling, model average, or don't look at all possible subsets with observational data unless you're doing prediction. Okay, so we're still kind of okay. But if you're not doing prediction in your other work, you should be really like cautious about this, right? Because that's what they're speaking to that audience. Okay, but there's a little bit of an out for us here, right? Because it's, in their opinion, this is sort of somewhat legitimate for prediction. For prediction in this context, we recommend model averaging. That is, a prediction is made with each model, and the Akaike weights are used to compute a weighted average of these predictions. Okay, so in the situation I've described in which we have a number of covariates and we don't know which one to use, I described shrinkage operators. Burnham and Anderson would say, okay, fine, you can throw everything but the kitchen sink at this and look at all possible models if you really are doing that. Like, it's like, okay, but when you're done, and after you've done that, do model averaging, where all these models are weighted by their relative Akaike information criterion. I'm not really going to talk about what AIC is, Akaike information criterion. I presume many of you have been exposed to it, but it is essentially a trade-off between model fit and complexity. So it uses theory, information theory, to come up with a balance between fit and complexity to avoid the overfitting problem that I've described earlier. So you can calculate with most models, not the neural networks, nothing. If it doesn't have a likelihood, you're never going to get an AIC. But for models for which there are likelihoods, an AIC can always be calculated. And so then we can do some weighting. Okay, the next slide is going to be a little bit gnarly, but I just want to point out what this looks like. This is just Burnham and Anderson again. I should go into viewer mode like this. Yeah. So the model average predicted estimate. So this is the little hat is the estimate, the prediction. The bar is the average. So the expected value of our response variable given some vector of inputs is the sum of our individual expectations, but just with this weight, right? So this weight again comes from just the AICs. It's arithmetic. It's very simple to get these weights. But there's this further need to look at, is this predicted? So for the particular covariate X, is it even in the model, right? Because we're talking about looking across all possible subsets of this model, right? Like, so maybe one particular model doesn't have PDO, Pacific Decadal Oscillation, is not in it. So if it's not in that model, then that model contributes nothing to the weighting of Pacific Decadal Oscillation. And so this is fancy looking math, but all it's saying is that ignore the covariate if it's not in there, right? So when you get down here to this term right here, this is a 1 or a 0, depending on if that focal variable or its associated coefficient is in the model or not. So if it's a 0, it just goes away. If this term, which is weird because it's I parentheses G, but if this thing here is a 0, everything's gone, right? Zeroes out everything. So it contributes nothing if it's not in the model. That's really all this is saying, right? Looks really advanced, but at the end of it, it's actually really simple. Yeah, so this is the way in which you come up with these model averaged estimates of the coefficients, right? And then you can use these to make your predictions. There's another little interesting note here at the end about the weights, but I think I just want to reiterate what Burnham and Anderson would think about this and how to do model averaging. This is, again, using Akaike information criterion, which means this is frequentist, not Bayesian. Bayesian's actually, in some ways, they have more options for how they can do model averaging, and I'm not really going to talk about them, but I will describe one more technique for doing model averaging, which I think is very interesting and relatively underutilized. And it involves Bayesian stuff, but I'm not going to really introduce Bayesian. So here's the idea. And it requires us to use reversible jump Markov chain Monte Carlo, which is a way of implementing Bayesian models. But the idea, and so there's software for this. So you don't even have to know what this is. You just got to know what software to choose. And then this can happen for you. But here's the idea. I've used this equation many times. This is the Beveridge-Holtz-Spanner recruit model, just a nonlinear function. And then up in an exponent, we previously had the error term. Well, it's right there. And that's up in an exponent. I don't know if you can see it, but that's up in an exponent. So we had that error. We saw that previously, normally distributed, but up in an exponent, which means this is log normally distributed. And so we can just start piling in covariates. And they should also go up in the exponent. And the reason you know that is because your error term is already exponentiated. And there's theory about why that's the case. It has to do with multiplicative survivals. It's beyond what I want to talk about. But if you see that the error term was up in an exponent, this should probably key you into thinking about piling in your covariates there as well. And all this is doing is just adding them in one plus another. So you could, if you wanted, include quadratic terms and interactions, and it's kind of complicated because it's all up in an exponent, but you can still do that kind of a thing. So this is just a traditional nonlinear model, I guess. There's nothing fancy happening yet. And in this case, we're just entertaining 3 covariates, and maybe you have 25. Okay, so if you have many, and it's just too cumbersome to write them all out. So just imagine this continuing on off to the wall. If you have many of these, think about doing model selection like this. In front of every coefficient, you have a new term z, which is either 0 or 1. So much like in the Burnham and Anderson stuff where that term was a 0 or 1 and it just turns stuff off, we're doing the same thing here. If z becomes a 0, this whole thing here becomes a 0. E to the 0 is 1. 1 multiplied into this is itself. So whenever z goes to 0, this term just shuts itself off essentially, and we're left with everything else. And so we can do this for any number of potential covariates that are in our model. And what some of this subscript notation is showing us is that we're going to draw these random variables uniquely for each one of our covariates. And so they all are going to have some initial probability of being included in the model. So this is where a prior is. And a reasonable choice, well, I don't know if it's reasonable. We can have discussion about this, but a uninformative choice would be to choose a beta distribution parameterized with 1 and 1. So this is basically a flat probability distribution, which gives equal probability to all possible values between 0 and 1. So the probability of this covariate being in the model is not informed by our choice of this P, but some numbers got to basically get put in there, and we're just saying draw it randomly and uniformly between 0 and 1. So we're not prejudicing the inclusion of any variable over any other variable. We're saying they're all equally likely, and they all have essentially an equal probability of being in the model. But this is kind of neat. Like, I think you can maybe imagine some scenario or kind of picture it in your mind of, we're just getting 0s and 1s, and we're using it to turn terms on and off. And the reason we have to do this with reversible jump Markov chain is that we have to have these choices of these z's all be independent of each other. And MCMCs don't often just give you that, but reversible jump will. So we can draw these, the z for this and that, and all of them, they will be drawn independently from one another. And the corresponding values of the parameters are going to be unaffected by the choice of the z's. Let me just show you an example of this. I'm going to simulate some data in which the true values for beta 1 and beta 2 are given here, and beta 3 is not going to actually be used. Okay, so I'm going to generate a random number here, but when I create the actual data, I'm going to put this number here to 0. So basically, I'm going to turn this whole thing off. So this is going to be like a fake variable again, right? So I'm going to generate a data, but not use it to create data. I'm sorry, I'm going to use this variable. I'm going to create this variable, but I'm not going to actually use it in the actual thing we're trying to predict. And then I'm going to put that variable back in, and I'm going to ask, does it get chosen by this technique, or can this technique realize that this variable was never actually used to generate that variable? And then I'm going to vary it over different magnitudes of uncertainty here. So as we get more and more uncertainty, what happens to our ability to correctly identify if a given variable is in the model or not in the model? So here's what that looks like. We're just increasing the uncertainty in that that data generating process. And then we're looking at the covariate inclusion probability for the 3 variables. One of them is plotted on the x-axis. So this is actually good. This is that third variable. And it was the probability of including that variable was 0 across all levels of recruitment uncertainty. So it never thought that the third variable, which was truly not used to generate the response variable, was never selected to be a part of this. And the variables which were actually used to generate the response variable were selected 100%, like given 100% probability of being predictive when we had low recruitment uncertainty. But as we add more and more noise to the system, the probability of selecting those variables starts to go down. And you can see they're not the same. And I think I got to remember which one's green and blue. The green is going to be this one because it's just a larger magnitude. So the first variable had a bigger effect than the second one because the magnitude is larger, it's twice as big, basically. And that's why this is going to be for that first variable with a 0.4 coefficient, and this one is for the negative 0.2. So it's not as big, and thus it gets dropped more quickly, right? Its effect was not as large. And so as you get more and more noise, it gets harder and harder for the model to find if that variable was significant or not. So I think that this is a really fun way of doing model averaging in a scenario in which you have no real good a priori hypothesis to narrow down your set of candidate variables, which is something you should always be thinking about. But if you have nothing further to base your model selection on, and you're in this situation of everything but the kitchen sink, here's a way in which, in a Bayesian framework, you can do model selection on all possible models all at once. Kind of fun. One more slide. This is just to prove that this technique doesn't actually lead to any bias. And so here we're getting the parameter estimate, in this case for the parameter 1, beta 1 and beta 2. And the estimates are in black dots with 95% CIs and red lines. And so as you get more and more uncertainty, the uncertainty around the point estimate for beta increases, but there's no bias in the estimates, right? They're always popping out pretty much right on the line. So this process of adding this indicator variable z, 0 and 1, didn't bias the estimate of our coefficient, which is cool. Because of those shrinkage estimators, they are intentionally pushing those coefficients closer to 0 to avoid overfitting. This doesn't do that. Right? This is just telling you what's the probability that it's in the model versus not in the model. And then if it's in the model, that's what this conditioning is saying right here. The value of the coefficient, given that it's in the model, what is its value going to be? And it's totally clean from the indicator variable process that we added. It's neat. I think that's so cool. All right, I'm done. But before I step down, I guess we should open this up for question, comment, discussion. Yeah.
Do you ever go out in the field, or are you just an analyst?
Yeah, I'm just an analyst.
Just, are there people online, if you could just repeat the question in the microphone? Go right here.
The question was, do you ever go out in the field, or are you just an analyst?
Yeah, and I'm not really a field biologist. Anything else? Yes.
I apologize if I missed this, but how robust would a method like this be to collinear variables? Or do you have to do like a DFA first?
Yeah, great question. It should be robust. I don't know. It would be very easy. I've already coded up a test of this. But these variables were all independent of one another. Man, I don't really have a good intuition for this, actually. The more I think about it, I'm not really sure how it's going to trade off putting in one variable versus the other variable when they're collinear. I presume you would not get a situation in which the z's were both turned on at the same time. So it would either pick one or the other, but probably not both. But I don't actually know. But I know how to test it. But that's a great question. Yeah. All right, we'll let Mark work his magic.
I'll start with my answer to your question. Yes, I do go into the field. Okay, so what I'm going to do for roughly the next, let's see, must be about an hour, is talk about two sort of different approaches to kind of underlying models in a forecast context. Both of these have been used in many instances. The second one that I get to is much newer and has a less of a history to it. But there we go. Okay, so the first one is state space models. Quick show of hands, when people hear these words, does this mean no, meh, or I'm down with this? Okay, I got some thumbs up, some mehs, and some downs. All right, perfect. So those of you with thumbs up, maybe this will be review, but otherwise, so let's just think about a situation that, well, Matt and I and probably many of you deal with, and this is ESA, Endangered Species Act. Every 5 years, ESA mandates that agencies who are charged with the recovery of those species conduct status reviews. And this list of things here is basically all the things that a status review team needs to think about. And in particular, most of this information is not pure, meaning it was not handed to us from Darwin or God or somebody, right? But rather, it's stuff that we gathered. We went out into the field and collected this information, wrote it down in a Write in the Rain book, came back, and hopefully entered that into some data frame. So the question then people say is like, well, I mean, we're dealing with endangered species, right? You guys must just be drowning in data. I already see head shaking. No way. This is the situation. This is what I met with. When people tell me that, oh, I'm like, I'm going to go now. The reality is data problems all over the place. This is not uncommon, right? Gaps in information, no funding, grad student overslept, boat broke, whatever I mean, these things happen, right? So data are gappy, they're noisy. I was talking with some folks at a coffee break who are trying to deal with this. Non-exhaustive surveys, undetected individuals, misidentified individuals. So we have problems when we go out and do this. Data are disparate. We get them from all kinds of different sources. We may have direct or remote sample data. We have design-based surveys, or we just have opportunistic surveys. People go when they can. Citizen science groups, this is becoming huge. Scientific surveys versus recreational sampling. It's not at all uncommon that we would use angling data, for instance, creel surveys, these types of things. So we have different kinds. So the question is, given noisy, gappy, different forms of data, how can we bring all of this to bear on a problem or a question we're trying to answer? And one option is a state space model. And so I'm going to go through this in some detail and try to motivate this with some examples later. But basically, there's two parts to a state space model, and the first is the state. And really what we think of as a state here is the true state of nature. So this would be what is really going on with the animals or the system of interest. And these states of nature can be all kinds of different things, right? It could be where are the animals on a landscape? Maybe we have the GPS collar on a cougar. Could be the number of individuals, the density, their biomass, age, structure, reproductive status. Any of things could be thought of as states of nature. And the changes in those states of nature are typically driven by two different factors. Some of those are intrinsic. So this is things like fecundity, size of the animals, these sort of things. And then we have all these extrinsic factors that Mother Nature throws at them in any given year. Is it cold and wet? Is it warm and dry? How's the habitat? All these different things. So some of these things are unknown to us as an analyst or a biologist, right? There are things that are going on. We just don't know what they are. We don't know what to call them. And so we didn't measure them and we didn't write them down. And we typically refer to these things as process errors in a environmental context, or state errors, you'll hear those. And basically they are affecting that underlying state of nature, but we don't exactly know what they are. They're driving some stochasticity, but what that is, we're unsure of. So given we have some true state of nature and we want to know what's going on, we actually have to get out there into the field typically and collect some information, right? So this would not be on something like a costume ball. Everyone's got all this stuff on. There's a real person underneath all of this regalia, but you don't know who that is. So you got to spend some time observing what's going on. So different sampling errors or observation errors, I'm going to use these two terms interchangeably, depend on many different factors. And probably everyone in this room has dealt with almost all of these, if not all of these, right? Environmental conditions. So we're out flying an airplane, trying to do fixed wing surveys of some rivers or streams. It's cloudy. Okay, that's going to affect our ability. Behavior, things hear the airplane coming or they hear you walking up the stream and they're running away or swimming away. Demographics. So older ones may be less cryptic than juveniles. Sampling design and coverage. Are we doing a complete survey of this entire room, or are we only surveying this front table here? And then the observer skill, and a lot of folks have probably dealt with this, right? People get better at doing this, whether you're counting plankton under a microscope or counting reds out in the field, these sort of things. So in some cases, observing nature can be relatively easy. I did my dissertation working on sockeye salmon in Alaska. You park me up on this hilltop right here, these things are sitting on reds, and I can sit there for 5 minutes and get a really pretty good count of how many sockeye are there. They're bright red, they're not moving very much. It's fairly easy. That's a fairly rare instance in nature though, and I'm sure a lot of you are imagining this because it can also be hard. How many mayflies are there in this picture? Right? How are we going to get it? So now we're down here, we're turning over these rocks, we're maybe scraping mayflies off, we're trying to estimate the surface area of the rock. There's no way in heck we're going to survey this entire river. So we've got some sort of sampling or observation error induced just by surveying these animals themselves. So that brings up the second part of our state space model, and this is what we call an observation or a data model. And it really just means the data, that stuff that you wrote down in your Write in the Rain book, is simply equal to that true state of nature plus or minus some observation errors. And remember that these errors can be large in some cases, or they can be small, and there's lots of different contributing factors. So these methods have been used in many different fields. Aeronautics, this sort of thing, I'll talk about it briefly at the end. Finance, people use these all the time for forecasting. In finance, this is pretty small because banks do not magically lose money. In ecology, these things are big, okay? So just be aware of that. The relative magnitude of these can vary along things. So the way this works is we've got this true state of nature marching along through time, and every once in a while we show up and observe it. And you can think of this, I'm coloring this true state blue, and then we have some sampling or observation errors red. Together, those make purple. So if this is, not much error, this looks blue. If this is a lot of error, it looks quite red. Okay, why on earth would someone go through this trouble? Well, we've already talked about this a bit. You can combine many different data types. Changes over time in observers or sensors, varying survey efforts and locations, direct, remote sensing, et cetera. All of these types of things can be brought to bear in the same model. Missing data are easily accommodated. This happens all the time. Very rarely does somebody have a really complete census over long time periods. You may have blocks that are good, and then there's some missing information, then blocks, or maybe it's just random, but this happens. This does not break this system at all, because that true state of nature is just going to keep marching along whether we're there to observe it or not. The more NAs we have here, the more missing data, the less our ability to uncover this true state of nature. So having better coverage here gives you a better idea of what's going on. And if you can imagine, again, this is time, it could be space. Here we've got an observation, here we've got an observation, here we don't. So our uncertainty about this true state of nature is going to grow whenever we do not sample it. So if we had a string of missing values, our uncertainty about that thing is going to get larger and larger until we get some data, and then it will help bring it back together again. If you do this for multiple individuals or multiple sites, multiple species together, kind of in the same framework, you get much better accuracy and precision by doing so. And this has been well demonstrated with simulation and in individual applications here. The other one that's really important for a lot of us is what some people in the stock assessment literature refer to as the Robin Hood effect. That means the data poor will benefit from the data rich. So there may be some systems where you are that are surveyed every month, every year for decades. And then there's some where it's like, man, that thing is so far remote, we just, every once in a while, we backpack in there and we get that. Those that have relatively little data or where errors tend to be large will benefit from those other systems where you have much better data. Okay, so in general, the way these things work, and there's going to be a little bit of math here, but it's relatively straightforward. We have two models, a state model and an observation model. Generally here, we consider our state models to be autoregressive. And all that means is it's a function of itself. So some state at time t is just a function of the previous state. plus some process error. Now, in this case, I'm lumping all kinds of covariates into that process error, some of which we might know, temperature, flow, et cetera. But you could just think of this as a generic case we don't. The observation model here, these are the data. This is what we own. This is going to be a different function, G, of those states and that observation error. So when the observation error is very low or all but zero in the banking situation, the observation just equals the state. And when this is really big, those two get very far apart from one another. So I'll show you a little bit as to how this works. So here's a couple of different versions of state space models. The most simple in the world is a random walk observed with error. And a random walk model just says where we are today is where we were yesterday plus some process error. And we typically assume these to be normally distributed. And then the observation model here just says that true state is what we have in our pocket plus some observation error. In general, random walks do not make a very good forecast model, but as you've heard a little bit, they can be, because in a forecast context, what we know today, or you could think of this as x is t plus 1 is a function of x of t, your expectation or your guess would just be what this value was. Because nobody knows what this is, we have to estimate that. Okay, another version. So here's, some simulations of random walks. So all of these started at about the same point here, and they're just wandering off into space. And this is really common. And if we ran this axis out into infinity, here's a fun fact for you. You can get a lot of points at a cocktail party. A random walk will visit every bit of this entire line. So they will wander off here, and then some point they'll come back, and they'll be way down through the floor, and they'll be way up through the ceiling. That's all they're doing. And that random walk is just, it's sort of, people have also referred to this as the drunk guy stumbling home from the pub. Generally trying to go this way, but there's a little bit of this, and then there's a little bit of that sort of thing. But in general, they're headed in one direction. Next form is a biased random walk. So in this case, we've got a bias term here. The other way you'll hear these referred to as a random walk with drift. That's what geneticists tend to refer to them as. And in this case, the state today is still a function of yesterday, but then we've added this bias term. So this is just a constant that we're going to add or subtract at any given time. And this observation model has not changed at all. So here's some examples of that. So here's one where there's positive bias and here's negative. And on average, these are tending up or tending down. But importantly, they're not monotonically doing so. They're not going down as just a straight line or up as a straight line. And some of these, you can see this one went down for a while and then it's kind of bouncing around like that. This one went down and up, but this, since I simulated, I know that that actually has a positive bias term in there. So if you let these models go over a long period of time, they're not going to go way up and way down all over. They will tend in a certain direction, downward or upwards. I don't have any more detailed slides. This in log space is a very simple model for exponential population growth. So something you learned in like Bio 102 or Ecology 101. Complete analogs here. The last one, which you will probably run into and are used very often, are what are called mean reverting random or autoregressive models. So now, rather than just adding a term here or this, we've added a coefficient here. And so we're going to, today's value is some multiplier times yesterday's. And we typically assume that this multiplier B, here I'm calling it, the absolute value of which is less than 1. And what that means is any time, and do I have this? Yes. Anytime there's a deviation away from sort of this long-term mean, which is 0, that series tends to be pulled back. And that's why we call it mean reverting. In this case, the mean is 0. The mean could be 1,000. But the idea is that as we move away, we're pulled back. The smaller this value is, so the closer this gets to 0. So imagine the end case. This goes to 0. This whole term goes away, and our state is just white noise. So it just looks like a fuzzy caterpillar climbing across a stick, right? It's just all this stuff. as this thing approaches 1, this value goes to 1, that's our random walk. That thing will wander off all over the place. So in this case, when I simulated these, that value is about 0.5. So if it was 0.99, this would look way more like a random walk. It would wander off all over the place. If it got really close to 0, it's just going to look like white noise here. This, which you'll see later if we have time, is a density-dependent population growth rate in log space. A Gompertz model, basically, for those of you, which is really similar to a Ricker model. So here we have a very simple process model that we can modify just slightly to model actual population dynamics based on underlying theory. So we're not just throwing something that's purely phenomenological. There is sort of an ecological underpinning for why we would use these. Okay, let's consider for a moment, here's a time series, 30 data points. Start here, they bounce up, they go around down like this, and we're now going to analyze this because perhaps somebody has now said, we need a forecast for point 31. So before we generate our forecast, we need to have some sort of model that we can use to come up with a forecast. So let's consider 2 options here. Number 1, linear regression. Matt was just talking about this. Could be, I mean, look at that. Yeah, maybe there's a downward trend here. I'll buy that. The other one, we're going to use a biased random walk. So here's that autoregressive part, and then here's our bias term. And we can estimate the parameters for both of these models. Let's start with linear regression. And I'm just going to write this out as a state space model. So here our state, x, is equal to alpha plus beta t. And then the observation is that x plus vt. So hopefully you can just imagine, just substitute that in here, and y is alpha plus beta t times vt. Okay. And if we fit that model, this is what we get. So here's our fitted line. It's linear regression. Here's a straight line that is monotonically decreasing. Okay. If you think about the errors in this model, there's only one form, and that's an observation model. They're deviations away from that expectation. That's these red lines here. And if you stare for just a moment at those red lines, does anyone see anything that strikes them? Yes. Yeah, so maybe one way is you have a string of negative values, then a string of positive, then a couple, then these long string of positive and a long string of. Does anybody remember enough from linear regression analysis to know that term IID? Independent and identically distributed. Independent means there should be no relationship between these values from one time step to the other. They should just be white noise. And in here, there's very strong autocorrelation in those errors. Okay, so we have fundamentally violated the assumptions of this model by doing this exercise. Okay, now let's think about our biased random walk as a state space model. So here's our state model. Got a bias term. It's a function of yesterday. And our observation model is super simple. It just says, well, the observations are the state. There's no observation error right here. So let's fit that model to the data and see what we get. There it is. It fits perfectly. I'm done. Good night, mic drop. Okay, so now the question is, well, what do our errors look like here? In this case, we don't have observation errors. We have these funny process errors. So basically what happens is we started here, and there's a bias, and in this case, it's 0 minus 0.2. So it said drop 2/10, and then we're adding or subtracting some error. We ended up there. Then we dropped 2/10, and we added some error. Then we dropped 2/10, we ended there, right? So these red deviations here now are process errors. Deviations away from a process. And if we looked at the correlation of these, we wouldn't actually see that pathology that they're negatively or positively correlated over time. These errors are generally assumed to be independent. And they would. We could test this formally. Okay, so now I've shown you 2 extreme cases. One was an observation error only model, that linear regression, and the other was this process error only model, this biased random walk. Now what we're going to do is we're going to consider a hybrid of those two. So what if we just combine them? So now we've got our biased random walk here, just like before. And now our observation model, we've added some additional variation here owing to our inability to sample this system perfectly. Okay. And if you fit that model to these data, you now get this blue line here. And this blue line is a combination of both process and observation errors. So if we consider looking at our process errors again, oh boy. Oh, I see why. This is where the truth was. There's X0. We dropped down on our bias, we added process error, and now we're sitting here. And so on and so forth. Then, once we've gotten to our state, we've added these additional observation errors or subtract those. So if you consider the net of this red line and this gray line, that's the gray is the process error and the red here is observation. So every single one of these points is a function of both observation and process error. Okay, so that's basically the sort of the miracle, if you will, of state space models. They will allow you to sort of deal with both that observation error, our inability to perfectly sample the system, and that process error, the things that's driving the temporal evolution over time that we just don't know about, and we're trying to estimate. I've shown you this in a univariate context. This whole thing will expand to a multivariate context. So imagine we had multiple Ys here. We had data from many different streams or many rivers or across the entire west coast of North America. We could fit these sort of models. And this is done all the time in many different circumstances. The other thing that I'll mention just briefly is that the form, I'll just back up here quickly. This form can be expanded considerably to incorporate a lot of other aspects, as can this form right here. So I haven't showed you any covariates here. There's no predictor variables here, nor were there any predictor variables here in this example, but it is entirely possible to do so. And in fact, it is very common to do so because we often have really good reason to believe that there is something that is driving this underlying process. We're dealing with fish. Fish are cold-blooded. How about temperature? There's a good one. We have a situation which is prone to low flows and high flows. We have dewatered areas and scour. Putting flow in here is a good idea, right? Those sort of things. How about in this observation model? You could imagine all kinds of things that might affect this. Cloud cover. I mentioned temperature up here. I've worked on some reptiles in Texas. Temperature actually ends up in the observation model as well, because oftentimes those are trapped using pitfall traps. So they're basically coffee cans that you bury in the ground and the lizard runs along and falls into it. If it's cold, lizards don't move. It's hard to catch them if they're not moving. So you can imagine there's situations where the same covariate might show up in both sections of that model. This is another place for us to just pause for a minute, take that deep breath. And before you jump right into this, I spend all kinds of time chatting with people. Remember earlier on in our life cycle of things, who's involved and what do they know, right? Very often the biologists that are associated with these areas have a really good suspicion as to what's going on. So conversations with those individuals will give you some at least candidate set of covariates that you could add into your models, and then using all of those different methods that Matt was talking about, consider whether or not their inclusion improves your forecast or it just adds complexity that's unnecessary. So we always talk about this a lot. I have people come to my office all the time like, hey, Mark, I got a question for you. I'm trying to do this, that, and the other. I'm like, I'm sorry. Here's my whiteboard. Let's spend some time talking about this. And we talk about all the ecology and the underlying biology before we get to the math. So all of this fancy stuff that Matt and I are talking about all morning long is no good if you don't have a basal understanding of what it is you're trying to do, what information is available to you, and how it could best be used. Okay, let's see. Oh, this is a question that comes up all the time. How is it possible that you can parse this gray error from that red error in all of these? Well, it turns out that they actually have different temporal patterns. So here's a situation where I have taken 3 different realizations of the same process. So this is just a biased random walk. And I had the exact same parameters and I just simulated it 3 times. All of them started at 0. And you can see that this one, yeah, these 3 look a bit different to me. In this case, it's the same process that I just added some observation error to, and all of these tend to look much more similar to one another. Now, here's another problem that people often have. Our eyes are terrible at statistics. Trust me on this one. So if you don't believe me by just looking at these, yeah, the computer is going to do this for you using some fairly clever algorithms. So you don't have to just eyeball these and say, oh, that's all process error, that's all observation error. It can be extracted. Now, the relative amounts of these will make that different. You can ask Kevin about his PhD dissertation. He demonstrated this in great detail when it came to PVAs. So the relative magnitudes of these things will affect what's going on. There's ways to help you do this. Can you get multiple observations of a state? So I've been talking about a situation, just back up one more. We have one underlying state we're trying to uncover, and here I've sort of expressed this with one observation. You could imagine a situation where we go to multiple locations on the landscape or multiple sections of stream, and those observations are all different and will collectively tell us something about that underlying state. So multiple observations really help identify what's this variance term here and what's that variance term. The other thing we talked about, like in a Bayesian context, is there other information available to you? If you're doing all of your stuff based on mark recapture assignments, there's a pretty good idea you have an idea what that estimation error is based on the method that you're using or that somebody else has done it ahead of you. Different system. So, you know, maybe someone in Idaho has done some work on this. We're working in Washington. Oh, we can turn around and look at what they've done and we could use that information. Imagine now this is, here we're using a piece of machinery, a gas chromatograph or a mass spec. We're looking at isotope data. Chances are really good on the side of that mass spec, if we turn the thing around, there's a little metal plate stamped on there that says something like the precision of this machine is plus or minus, 0.2 del units. Okay, now we don't even have to estimate this thing. We can just stick that into the model. Okay, so there are ways to sort of beat the system, but at some point, you will inevitably run up to a situation where this is hard to do. It can help overcome all those deficiencies I stated at the outset, but it is not a panacea. There will be situations where this is just very difficult. For instance, when the magnitude of this is a lot larger than this, that can be hard to do, right, Kevin? Guess what, in ecology? These are almost always larger than these. So that's why, like I said, multiple observations, this sort of thing can be useful. The other thing that I alluded to is this could come from snorkel survey, e-fishing, mark recapture, you have multiple data streams that can be brought to bear on these situations. Okay, and I think that's, I do want to talk just briefly about the Kalman filter and some of the output in it, because the software that we'll talk about if we have time uses this. So back in the 1950s, this fellow Rudolf Kalman became really interested in a problem for trying to obtain signals from noisy data. And he was actually really interested in this from an aeronautics perspective. This is when the space program was really starting to balloon. And the idea is if we shoot a rocket off into space, how the heck are we going to know where that thing is? We're going to get some estimates from it. I mean, at some point, there's people on the ground with binoculars, and then it's gone. And then we're dealing with radio signals, pretty much. Okay, and this is the 50s. This is a long time ago. So at some point, he visited NASA and was talking about some of these methods there, and the people there said, you have the solution to our problem. So they basically adopted what he had, and they built those into their navigation and guidance computers into the Apollo missions. Fun fact here, my laptop has 8 million times more RAM than these computers. So let that sink in. Anyone seen the movie Apollo 13? I mean, they got that thing up there, it broke, and then they got it back. How wild is that, using this thing that had, like, I mean, it's like, you know, two squirrels and a coin they're flipping in there. You know, I mean, oh my gosh. Anyway, now this Kalman filter is widely used in lots of different fields: statistics, aeronautics, robotics. They're doing this all the time now. So very old criteria, and there's ways of doing this. There's lots of different software that will do this for you. The big one is expectation maximization is sort of the gold standard right now, but there are other ways of doing this. One of the things to be aware of, though, when you're considering this, is that the Kalman filter produces 3 types of estimates. So as it's trying to do this, it's time series, so it's marching along through time, and it does produce a prediction. So at some time t, we don't know what this value is yet, it will give us a prediction of what it thinks that is. And then this value is observed or passed to the algorithm, and it's updated to describe what's called a filter. Then it gets finally to the end of the time series. This algorithm marches back and runs backwards and smooths all these estimates out. So in most applications of state space models, if you're reading these in the literature, that sort of thing, what you're seeing are these values reported. But what you have to be really conscious of in a forecast context, this is not your forecast. This is your forecast coming out right here. And the software should allow you to do that. The software that we use and is developed will definitely produce that for you. For those of you who have slides, these are all hot links actually in here. You can click on any of these. This is a class I teach with some colleagues at UW. Lots of information there. We have an ebook. We have a YouTube channel with all kinds of videos on it. So if you want to learn all about state space models, I would encourage you to check those out. And I think that's all oh no, here's another one. This, I believe, is the last slide. This is a review paper from a couple of years ago. Marie is a professor in the statistics department at UBC. These are a lot of people that collaborated on this, and this is a very approachable paper for time series analysis. These are statisticians, so there's some stats in here. It's long, it's in monographs, but it is a really good overview, so that would be another source of information for folks. And that is, in fact, the last one. So let's see how we're doing. Questions about that? Great parlor trick, isn't it? No, nothing? Well, you all have my contact information, so folks can track me down if you'd like. Okay, what I'm going to do now is I'm going to skip in your materials here. There's an R exercise. Let me just show you this very quickly. If you'd like to, on your own, go through this when you get back to your desk someday, there's a whole bunch of information that walks you through how we get to sort of those AR models. Here's that really simple one, sorry. Here's basically that simple one I was showing you again. That's in log space, this Gompertz model right here. Anyway, I go through a bunch of exercises here, shows you how to fit these models using some software. There's some bit at the end about forecasting and how you can get that information out. You can see this is actually a forecast with some uncertainty envelopes here. So anyway, like I said, for the interest of time, I'm not going to walk through this right now. At some point, you folks can track me down and we could do it together if you'd like. But anyway, just be aware of that. Let's see back here. Okay. All right. I want to just spend a few minutes now talking about what are called integrated population models. This, in my mind, is really sort of the state of art of forecasting right now. They have been around in different flavors for quite a while. They're relatively new to, I'll say, the freshwater side of fisheries science. Stock assessment folks have been using these for quite a while. They don't call them integrated population models. They call them some form of bizarre stock assessment model. You have to actually, they all get their individual different names. People who've been working on birds, reptiles, amphibians have also been doing this for a number of years. But basically, the way I'm going to motivate this is talk about, first of all, run reconstruction. Everyone, if I say those two words, someone have a general idea what it is? It's building a brood table, right? Sean alluded to earlier that someone's do this. So let's talk about building a brood table. Here I've got several columns. Here's the year, number of returns, ultimately recruits, and then different age classes. And what typically happens is we get some estimate of our returns, and then we know something about the proportions of different age groups based on sampling in a fishery or otoliths, scales, something like that. And we just multiply those proportions by this to get these number of returns at different ages. This should look fairly familiar to everyone. And we go through that exercise and we start filling this thing in. Here we've got up through year 8. And now we can basically calculate the number of recruits based on this. So here we have 3 years fish here, 4-year fish here, and 5-year fish here. You add those up along the diagonal, that gives you your recruits there. Okay, and you just go through this exercise. But at some point, you're going to get to a point here where we're dealing with incomplete returns. So that's an incomplete estimate of recruits. Here's even less complete, and we have nothing right here, right? Because we just haven't seen those fish come back. Smolts went to sea, adults have yet to return, so we don't know what's available to us. Once we've got these, then we take our column of recruits. Well, here's recruits, here's our stock or return, and we just pass those to some stock recruitment model. Ricker, hockey stick, Beverton Holt, things like Matt was showing earlier. Problems with this approach, though. First of all, spawner counts are almost certainly non-exhaustive. Now, there are some exceptions. There are some systems that have weirs, and they do a really good job of counting them, but most weir-based systems still do not get a 100% accurate count. Okay, so we have problems here. So let's think about our Ricker model. And what people often do is they'll linearize this. They take the log and rearrange a couple of spaces. And if you just do substitution, this Ricker model in log space is just a linear regression. And I mentioned an assumption in linear regression earlier about independent and identically distributed errors. Anyone know another assumption about this predictor variable in linear regression? Known without error. Okay, I just said this is that the analogy here is spawner counts, and almost all spawner counts contain some error. So here we've just violated the fundamental assumptions of this regression model. Okay, age composition are typically non-exhaustive and imprecise. So usually these are sampled from like a fishery or a few carcasses we've sampled on the spawning grounds, right? We have not censused every individual to find out how old they are. So what that means is that the fish from age composition are way smaller than the total return typically. So when you're calculating these numbers in here, that in and of itself is a model product, right? We have uncertainty in there. The other one is that in that situation, missing data present problems. So for some year here, we had no budget, no weir, no biologist, no money, whatever the case may be. We have no information here. And once we fill out our brood table, we end up with a situation where these are missing, and we can't compute recruits here, nor can we compute returns there. We just lost 4 pairs of data for our regression analysis. Okay, and if you only had maybe 20 to begin with, now we're down 20% of our data. That's not great. So the other thing to think about is that those underlying stock recruitment models, those are really meant to estimate the true state of nature. So that's really this sort of process model. It's not meant to be an observation model. It's meant to tell us if we put this many spawning females into a river, and presumably males aren't the problem, how many female returns are we going to get? So that's a process system. So in an observation model, like a linear regression, that time ordering doesn't matter. I can scramble every one of these rows up and I'm still going to get this plot. Okay, so the time ordering of the information doesn't help us at all, and we're actually just going to completely ignore it. Okay, so that motivates what are these IPMs. So basically, if you want to remember one thing from this presentation, this is it. When constructing this a model like this, whether it be for run forecasting specifically, or you're even thinking about a life cycle model, go back to steps 1, 2, and 3 on that chart we talked about earlier today. What are the data that are available to you and in what form do they come? Based on that, you should then be making your model match the data. Not sit down with a whiteboard or a piece of paper and write out the most detailed life cycle you can imagine for salmon, and then start trying to figure out all those different things that are going in those boxes and arrows. People do this all the time. I see some smiles in the room right now, but just be aware, this says this is done all the time, okay? So as an example here, here's a recent paper led by Mark Sorrell, who was a PhD student in our school. This is an IPM for Wenatchee River Chinook salmon. This is fairly detailed here, but all of this is based on information. There are either absolute counts or information based on marked fish that are tagged somewhere in the system and then recited at dams, okay? Here is a recent paper from Jeff Jorgensen, some colleagues for Chehalis. This was just dreamed up on a whiteboard. Most of this information they don't actually have. And now they're running around trying to figure out what things they're going to put in the boxes and how they're going to make the arrows. Okay, so what that leads to is this sort of situation. In an IPM, we use the exact same model for the fitting and the projection portion of this. And in standard, often these life cycle models, you use some way of building this model. You know, you throw everything in there. You've got this Rube Goldberg contraption. And then once you're done, you start cranking the thing to go forward in this. And these are two different processes. And typically what this means is that in this situation, any uncertainty that we add here is propagated through this entire process. So that when we get to the end and we have to report that uncertainty, remember that reporting bit we talked about earlier this morning? We have now an honest accounting of all the uncertainty that we're aware of. This situation, there's uncertainty here, all over the place in here. Now we get to here, it's a different beast. We have to sort of figure out how we're going to convey that uncertainty and where it comes from. And how well does this prediction part match the other part? So if you're thinking about the stuff that Matt was just talking about, you're kind of dealing with apples and oranges here, okay? Okay, so IPMs work like this. The first step is to create recruits from spawners. You don't get all this stuff and then back calculate this. So you have some generating model, like a Ricker model, that you use, and based on the spawners, you produce recruits. And we often do this where we even treat these process errors as autocorrelated, something like that. That's all this term is. You can add covariates in here. This thing can be as complex or as simple as you like. That's not a prescription. Here's a situation where we've added some covariates that have potentially lagged at some time. Maybe it's 4 or 5 years in the past. Then once we have our recruits based on that process model, we have to project those recruits forward at different ages. Okay, so now we just have a really simple model that says the number at some age is the proportionate age times those basically total recruits. And that's just fills out the columns of this. The other thing is that we're going to acknowledge is that our true spawners here are the difference between the number of returns and catch, right? So if we knew the true number of fish and we know the true number of caught, we should get the true spawners. Yes? Yeah, so that's an excellent question. Thank you very much. Let's now count these recruits as smolts. So now we're going to produce smolts from spawners in a process. That's our underlying generative model. And then we're going to use all that rotary screw trap data to ground truth how good these estimates are. Yep. So yeah, that's why I had said earlier on, when we were talking about kind of your laundry list of things, if you have intermediate life stages, you could definitely bring that to bear in here. Yes. It does not have to be spawner to spawner. It could be spawner to smolt to spawner. Yeah, in that example I showed that Mark Sorrell was doing, we have a bunch of juvenile outmigrants and stuff in there as well. Yep. Okay, so This is our true case, but we know that the measured escapement is really that truth that's been corrupted with some observation error. So now we have an observation model for spawners here. So this is what we have in hand. This is what we're trying to estimate. Then based on that, we can sum up the number of fish. Here, I'll just go this way and I'll even drop this last one in here. We know the total returns based on the individual returns at each age. And then we know the proportion of age by just taking each one of those age classes and dividing by the total. And we basically dump that into a multinomial model. And this is a bit abstract, but basically what this says is that if we add all of these things up, they're supposed to equal this. So now we have a process model that's trying to fill in these diagonals. And we have an observation model that's ground truthing this by saying, well, after you fill all these things in on the diagonal, if you sum across the row, you better get that number. So this is, okay, we dumped some things in here. Oops, we're too high. Now we have to pull some back, dump some more in. Oops, we're too low. Now we have to pull some back, right? So these two models are working with each other to basically fill in this brood table here. Okay, so by way of example, I'm just going to show you some work from Washington Coho. This was a paper led by Lucas DiFilippo, who was a PhD student several years ago. Thomas and Neil are with WDFW. Daniel and I are with UW. And the whole motivation here was to look at short-term, meaning 1 step ahead, 1 year ahead forecast for Coho and Washington State. And WDFW has been doing this for a long time. They have several different methods that largely depend on where. Outer coast was a little bit different than North Coast, was a little bit different than inside the Sound. And they were looking to see, is there kind of one model to rule them all? So the idea here was, let's not do this location by location by location. Instead, we're going to take all of those rivers together and do this under one large hood. And as I alluded to when we were talking about state space models, doing them all under one hood is going to take that Robin Hood effect we were talking about. We're going to benefit from that. We're going to benefit from age composition in some areas less so than others. Now this one again is relatively simple because they're coho, but there are jacks in here, so we're not doing with a totally fixed age composition. So here's the domain area. All these, here's outer coast, here's north coast, and then we have a bunch of areas here in Puget Sound. So for those of you who don't know, I'll go through this fairly quickly, right? Spawn in fall of year T, fry emerge the following spring. Most juveniles there are about a year. Outmigrate to as smolts in year 2+2. Most of them are there a year and a half. Some jacks or the occasional Jill is only out there for about half a year. And then they're back to spawn. Okay, so the data we had was from 86 through 2017. And some of the things we know are fixed, like the quantity of habitat. So there's estimates where they say, okay, this amount of stream length is what we consider to be suitable spawning habitat for coho. That's going into the model from a capacity standpoint. We have counts of adult escapement. We have counts of adult harvest. We know something about smolt outmigration for some of these areas, not for every single one. And we had coded wire tag estimates for marine survival. Okay, so here's a bunch of independent, this one is fixed over time. These are all time varying and space varying for that matter. Okay, so we originally fit this to 16 years of data, 86 through 2001, and then we're evaluating our skill over the following 16 years, with that model being refit every year. So we make a forecast for 2002, and then we refit the model, and then we make a forecast for 03, refit the model, et cetera. Okay, so this is getting at some of the questions that we were talking about earlier. We're using the mean absolute square deviance here. So this is the predicted, that's the observed. This is one of those values that Matt showed earlier. We could have used others. This is the one we settled on. And I'd be happy to talk about this in more detail later. We know that based on these coded wire tag estimates for marine survival, that some of these populations have very high correlations with respect to survival in the marine environment, and others very little correlation with one another. We brought this information into the model and we were thinking about those process errors. We built that in such that that covariance matrix now explicitly takes into account the distance that those river mouths we used in this case are from one another. So the idea here is that we expect rivers that are very close together to one another geographically are going to experience similar conditions in the ocean and to some extent in freshwater. Here's our theoretical parent-offspring relationship, Beverton-Holt for this case. Here's what the real estimates look like. So this is kind of funny for me because when you start talking about this thing, everyone expects that all these data points are going to lie right on here. Like an R squared of 0.9 or something. There's the reality of the situation. Here's all of our different populations or stocks you could consider. This is smolts per kilometer. So this is a similar situation that you were alluding to. We're using a Beverton-Holt to get from adult to smolt, and then we model that marine survival from smolt to return again. You can see some of these don't really look like a Beverton-Holt. Some just look like a shotgun blast, that sort of thing. The uncertainty in here is based on the process error only, and then owing to observation error as well. Okay. None of these are great fits. This is really the best we can do though. So presumably all the deviations away from this, assuming we have the correct model, is a bunch of that stuff we don't know about and we did not measure. It's all those process errors that I was alluding to. Here's our forecast scale, and I know this is relatively small. Basically what you want to see is that the blue areas where the model was fit initially, and this kind of amber color is where the forecasts are. The black dots are the observations, and these open circles with the bands are the forecast. So this one, yeah, maybe not great. That one's pretty good. That one's really good. That one's really good. There's others. Anyway, in summary, what we're looking at is something like this. So our example in here is these blue bars, and then you add on the black bar, and that gets you to what the current methods are. So in nearly all of these cases, we had an improvement in forecast skill by using this IPM. Not always. Here's some that we didn't do much better at all. And it turns out that some of these that we did not do much better at, a simple moving average model like Matt was alluding to in his presentation works pretty well. So largely just say, what was it last year or 2 years ago averaged, and you get pretty good results. So here's a demonstration of actually using all of this under one hood to generate better forecasts across a large geographic area. And I think that's about all I have. If you want to learn more about IPMs, I've listed 3 GitHub repos up here. These are all publicly accessible. If you access the slides through there, these are links again. Here's Mark's IPM for the Wenatchee. Here's Lucas's that I just talked about, and here's one that I did for Steelhead and the Skagit. And I think, yep, that's all I've got for you. So I apologize. I know that was a real whirlwind tour, but at your leisure, take some time to look through those results. Questions? Yes. Oh, wait, hold on one second.
Thank you. Yeah, first of all, I want to thank you for all your contributions. Your work is amazing, and I appreciate it, and the fish do too.
Thanks. I did not pay him, by the way.
It's true. We've never even met, so. I'm wondering, I know a lot of the data you feed into these models, the escapement data doesn't have confidence or credible intervals. If that was changed and they estimated those, how would that improve your forecasting in these models?
Yeah, so I'll go back. Well, oop, right here. If we had some idea as to what was going on, we wouldn't have to estimate this variance term. We could get these from the field-based surveys. And to your point, this escapement value is already sort of a model product for us. By the time I get that number, somebody has done a red expansion or something like that. So that's how we know all of this is in here. Ideally, this number right here came right out of that Right in the Rain book. And then we have a much more detailed model that gets us from whatever we wrote down in the book to an actual number at the river level. This is being done much more now, and you may know about some of this work in the Lower Columbia. Thomas and Kale and some others have been working on this with Eric Beal and some others. So they're trying to get down to that basal level. some of these situations too, I didn't talk about any of this, but like we have models in here where there's some animals are being removed for hatchery brood stock and a bunch of other things going on. So they can get even much more complicated than they are now. But the point is that whenever there's a box or an arrow in that diagram, we have numbers to put in there right now. We're not just going off to BC or Atlantic salmon from Europe or wherever and dragging those numbers in and squishing them in. Yeah, other questions? Yes. Oh, wait. Just throw it.
So I feel like people are trying to utilize this. One of the common things that people want to do is be able to turn the dials and use complex models to not only kind of forecast what to expect, but like for restoration, for example, like how do you turn the dials and what does that look like in terms of how many juveniles you expect to be produced out of the system if you turn the dial, so many, for restoration, improving habitat or survival in a hydro system and whatnot. So how do those complicate these models? Do you like what do you feel that that's a valuable way to use these models?
Yeah, that's an exceptional question. There's nothing about these models that precludes that type of analysis. So if in the case where you have covariates built in there, and that's largely what you're referring to, some of it may be harvest management, right? There's not a covariance, but yeah, you're going to pull that harvest lever, and when harvest is off completely versus rather liberal, if there are covariates in there, all those relationships can be built in, just like we've been talking about. And then all you have to do is change those as inputs, especially in a forward projection situation. Almost all of those that I'm aware of, people are thinking about what happens in the future if. There's always this conditional, if we do, and then here's your whole suite of levers and management actions to pull. Most of those, we don't know what's going to happen in the future, like from the covariate perspective. So we have to come up now with some generating model for the covariates. So in some circumstances, what we've done, like we did a big, an integrated model for Snake River Chinook. And there we were doing it at sort of the population level. So there's 22 different groups. And we don't know what climate is going to be doing in the future. So we just had a really simple model for climate. And it was a very simple autoregressive model that we used to do that. And that nice thing about that is once that's, we can just simulate that into the future, like I was showing you earlier in the state space thing. And in that situation, we don't know which of those is going to be true. So we simply just took the expectations after some time period. The top third were good, the middle third were neutral, and the bottom third were bad. And then based on the results using those, we sort of said, okay, if we think climate's going to be poor, here's what we would expect. If we think it's going to be roughly neutral, here's what we'd expect. If we think it's going to be good, here's what we'd expect. So you can still game, there's nothing different inherently about those ways you would do it. It's still sort of that scenario analysis. You got to say, okay, if we change this, what do we expect? So it can certainly be done. These models are all done in Bayesian frameworks. That's really the only way to get this machinery to work. And there you have that ability to use priors. So you can really start to drive that with priors as well. We could sit down in a room like this, and I could ask every one of you, how do you think smolt to adult survival will change in the next 20 years? You give your number, and we put all that stuff in, and we just turn the crank on this thing, and we can come up with a whole bunch of different expectations and examine those in sort of that scenario frame. But that's a really good question. I mean, that you're not alone in asking that question, and it's a really important one, I think. We have to have a pretty good understanding of how the complexity of the system we've built interacts with what we think we're learning from it when we're done.
Yeah, it seems like certain things make sense, and predicting that out is useful. And there's a certain point where it becomes a bit crazy. People want to use the output of some of these without really understanding.
I agree entirely. Yeah. Lots of modeling work in this thing. People are looking at what's going to happen 50 or 100 years in the future, as though, all that stuff is stationary. Like nothing, I mean, there may be directional changes, but you know, when the floor is not going to fall out, you know, the ceiling's not going to blow off. I don't believe that. Those kind of time horizons to just make me queasy. You know, how many presidential administrations are we going to have in the next 100 years? Congressional, you know, a lot of this stuff requires money. And we're never even going to see some of that. At some point, someone's going to be like, we're done. Breach all those dams, you know, these sort of thing. It's like people want to run their air conditioners. They don't care about salmon. You know, I mean, I'm making this up and I work for the government, so don't treat me as a spokesperson here, but there's realities. I mean, there's a huge social fabric to all of this as well. I mean, we as analysts kind of get thrown into the mix and often at the pointy end of the ship, but there's all those people behind us that, you know, are relying on what we're doing. Yeah. I tell you what, let's turn this over to Matt so he can have kind of wrap up, and then I'm happy to engage with folks over lunchtime or this afternoon or whatever as well.
Okay, so we have seen some techniques for assessing how well we can forecast. We've seen some fancy techniques for making what is perhaps the best possible forecast given the state of science. Now, what you gonna do? So I asked this question because as an applied statistician, I find that no matter what I do, I am drawn towards decision analysis. At some point, we need to have a confrontation between our predictions and the uncertainty around it with some sort of action. And decision theory is the framework for translating our science into actions. And it's a really rich area. And it's sort of one of my intellectual hobbies. I don't do this a whole lot for money, but it's something I think is very interesting. So I dabble in this. So let me just read this. You know, I think that at this point you have some sense of the fact that salmon live in this vast, diverse, and dynamic environment. And because they're difficult to detect, we have this real significant forecasting problem that may not really be perfectly solved by better forecast math. Right? We've talked about a number of techniques, including very fancy AI things, and there's no panacea. There's no silver bullet. And so what are we going to do? I think the best we can do is reduce the uncertainty in our forecast as much as possible with the current state of science, and then have an accurate accounting of our uncertainty in the forecast, and then roll that uncertainty forward into an actual decision. So what I want to talk about is an example of doing this in the case of forecasting and in a scenario in which we're going to set some harvest regulations in light of the forecasted abundance that we're going to get back out. This is a real toy example, and we can make it really complicated, but this is about as simple as we can get to get your head around this. And then if we have time, I can show you how to get this out of PowerPoint and into an actual model. And I have that here. It's going to be a real simple model, actually, but we'll see if we get time to get there. So we've got a table here in which we have like the truth over here. And I've just discretized abundance into these three categories, right? Low, medium, and high. But maybe we don't have to stop there. This is just for simplicity. So just acknowledge that this can get really complicated in terms of our actual abundance categories. But for now, we're just low, medium, high. And we're going to have a forecast. And the forecast, as we've seen, all of our forecasts are quantitative. There's a number with some uncertainty. But let's just, for the sake of simplicity, consider that the forecast predicts discrete levels, low, medium, and high. So a good forecast would work out such that when the abundance is truly low, the forecast would generally predict a low abundance. And what we're seeing is that when it's truly low, our forecast is 0.6. 60% of the time it'll correctly say that the abundance is low. But 30% of the time it'll say that it's medium, and 10% of the time it says that it's high. So our forecast is wrong. It's not perfect, right? 60% correct, 40% wrong. There's two ways of being wrong. Okay, notice that this all sums up to 1. All right, so what about when the actual truth is medium abundance? Well, we kind of have a similar situation. When it's truly medium, our forecast is generally saying it's going to be medium, but you know, you got 40% probability split on low and high, so it's also wrong sometimes. And then similarly here, it just happens to be the kind of the inverse or the mirror image of low is playing out here. Okay. Now, what if I so this is like, okay, this is not a great forecast, but you know, this is maybe indicative of many actual real world forecasts. It's not too farcical, I don't think. So what if we get into this situation in which this year's forecast comes out high, and now you're a decision maker. You're going to decide something about what kind of harvest level you need to implement. So you're going to want to know, what is the probability that the abundance is low? The forecast came out high. What's the probability that the actual abundance is going to be low? Some more information for you. This is the marginal probability of low, medium, and high. So this is just saying, all else being equal, what are the abundances? What is the likelihood of finding a low, medium, or high abundance independent of the forecast? We just look back at our historical time series, right? And this is just like, you know, yeah, you know, 30% of the time it was low, 40% high, 30% low, 40 medium, 30% high. Okay. Now, I think that this is an eminently reasonable question to ask if you're a decision maker. Somebody tells you, your analyst comes in and says, you know, our forecast is high. They're going to want to know, well, what if it's actually low? Because they don't want to over harvest. And you can tell them, well, look, you know, here's all my assessment of the accuracy of my forecast. And here's what we know about what generally happens independent of the forecast. So what's the probability that the abundance is actually low, given that the forecast is high? Is there a genius in the room? I feel like you kind of have to be that, but there is an answer to this question, and it's really just kind of arithmetic. So I'm going to get right to the punchline on this. Thomas Bayes figured this stuff out. So if we use Bayes' theorem, we can arrive at an answer to this question using just arithmetic. Okay, the Bayesian kind of stuff Mark was talking about, and some of the stuff I had alluded to, involves this I was talking about reversible jump Markov chain Monte Carlo, and there's various flavors of this. We don't even need to go there. Okay, this is a much simpler arithmetic that we can use to answer this question up here. And so I like this subject, but I'm going to go right past why this equation is true, and we're just going to jump to how we can plug these numbers in. So the question is, what is the probability that the abundance is equal to low, given that our forecast is high? And if we think through all this stuff and we plug in the right numbers, all the information is supplied in this table up here. So we can actually calculate it right here. And the answer turns out to be 0.103. All right, well, I feel like we're making a little progress. The challenge in the sense that you got to have somebody around who knows to do all this kind of stuff, but now you all know, hey, this is Bayes, right? There's a formula for this, and it's actually just algebra. So I don't have to do any fancy computing. It's just spreadsheet stuff. So it's literally just like you can plug in all the numbers. All right, well, this is really useful, right? Because now we can answer this fundamental question of what is the probability that we're going to find ourselves in this very egregious situation of the actual abundance being low, even though our forecast is high. But now let me just add another layer to this. And this is the last layer of complexity here. what harvest rate should you now implement? Given the fact that we can now compute that the probability, we can compute the probability of the actual abundance being low, medium, or high in light of your forecast and that forecast uncertainty, right? We know the probabilities now of it being all possible abundances, in our case, only 3, low, medium, and high. So now I ask, what are you going to do? How are you going to actually implement a harvest regime? Like, are you going to implement a harvest regime that corresponds to a low abundance, a medium abundance, or a high abundance? And to get at this question, there's one more piece of information we need, and that is the utilities or the perception of risks and rewards associated with promulgating a harvest regime that is correct and versus a harvest regime that is wrong. And you can be wrong in 2 ways, right? You can implement a harvest that is too high or too low, right? So here's kind of just a made-up example of what this could look like. So if the abundance is actually low and we implement a harvest that's low, well, we're going to reap 80 points of utility from this situation. Right? This gets into human cognition and the realm of social science and psychologists and human dimensions kind of folks who can kind of extract these numbers from people by doing choice experiments and various other social science things. My point here is that there's a cognitive value that's in people's minds, decision makers' minds, or even in society's minds, or our constituents, that can be measured and quantified by the right kind of human dimensions expert. And so I'll pull out a few other points in here. So if the abundance is actually high and we implement a high harvest, like we're going to get a lot of utility out of that situation. But look at the flip side. If the abundance is actually low and we implement a high harvest, we're getting no utility out of that. That's bad. Similarly, if the abundance is actually high and we implement a low harvest, we get very low utility out of that, right? But it's not the same. Right, so like there's 2 different ways of being wrong, like actually low and we go harvest high, and then it's actually high and we abundance low, we harvest low. So the way in which we're going to trade off over harvest versus under harvest can be expressed in a table like this. Okay, so now given that you work with your managers, the bosses of the agency that are going to promulgate a harvest regime, and you figure out what their risk tolerances are, you get this table. And now I ask, given that this year's forecast is high, what harvest rate should we implement? Right? One that corresponds. So like, this is kind of a weird question, right? But it'd be like, I don't know, you're going to try to do something to be conservative, kind of middle of the road versus kind of cavalier, right? And so the exact way in which this happens is details that I don't really want to get at, but I'm just saying that there's some harvest regime that could be implemented that's going to correspond to different abundances, right? So if you're doing MSY stuff like that, it'll tell you what the harvest rate ought to be. But I think that this is where our work in forecasting salmon becomes applied. This is why, I mean, you tell me, why else are we forecasting salmon? I feel like it's almost always that we can set up a harvest regime that's appropriate. We don't have foregone opportunity, and so that we don't overharvest, right? That's why we want to know. Maybe there's a few other reasons, but this is the main one, okay? So I think the question in green is legit. How are we going to do that? Well, it's actually quite simple from here. I've already shown in the previous slide how we can compute the probability that the abundance is actually low, actually medium, or actually high. And now we know the values associated with doing different things under different conditions. And so from here, it's a pretty simple piece of arithmetic. And all we're going to do is we're just going to look at the expected utility of implementing a low harvest versus a medium harvest versus a high harvest. And all this is the probability of the abundance being low, medium, or high, as computed from the previous slide using Bayes' theorem, and multiplying it into the corresponding utility. of each one of those situations. So you just do this arithmetic and you see which one of these harvest strategies gives you the highest utility. And that's the one you should pick. So it's pretty straightforward. I haven't actually ran all the numbers on this, but that's a way in which the harvest uncertainty, I'm sorry, the way in which the forecast uncertainty can get implemented in an actual harvest regime. Yeah.
Can you explain to me where the uncertainty in your forecast comes in? Because this looks, that top table looks a little more just like made a point estimate, how often it's wrong.
Yeah. So imagine instead of having low, medium, and high, we had 5,000 numbers, different, and each one corresponds to an abundance that's out there, right? And so like we were seeing when we were doing like the plots of how far off your forecast is, there's like a distribution of deviations that we have. So we can calculate from that type of analysis the probability of having different levels of abundance right out of the forecast. So, you know, if the forecast comes in low, what is the probability that the abundance actually turns out to be high? Like I think maybe my point is that it might help to think about this not as 3 discrete levels, but as the actual number down to the last individual. Maybe you can ask the question again too, if I think I kind of butchered that a little.
I guess, so if your forecasts were very precise, with that top table,
Yeah,
like the
Yeah.
diagonal would have really high numbers.
exactly.
Yeah.
Right. Yes. And the only thing I was trying to say, so that I should have started there, but yes, this would all just be ones and zeros in the off diagonals if you had a perfect forecast. But what's interesting as well is that we can look at so here's one in which it's wrong, and we're spreading probability out 30 versus 10 between these. But maybe if you have a really weird forecast, you know, it's like equal probability of it being, once it's wrong, it's just wrong, right? You know, but it's more likely if it's actually low to be, you're going to be wrong in this way more frequently than wrong in this way. So anyway, this is where I'm describing, like, we can look at the, you know, are you generally accurate, but every now and then you get a real flyer that's really wild and we want to minimize being way off? Or are we going to be like more concerned about situations in which we're generally always off, but it's off by a little, right? We can encode that kind of error into a table like this, and that's easier to think about when you have more than just 3 levels in there. Yeah. Yeah. Oh, yeah, this is a great question. But honestly, it goes beyond my area of expertise. But I think that people who work in this area will have a lot of opinions on this, and they might themselves not really be too coherent. I think what you would probably want to do is arrive at a social process of stakeholder engagement in which, you know, you get people to agree on these values, and then you run the analysis on the consensus table of utilities, as opposed to each individual being able to say whatever they want on this table and then average across all the people, right? So I think you know, it's a jointly managed, a jointly shared resource, and so you got to get the stakeholders to eventually agree on this, and then you have one implementation of the model from there. But a lot of time can be spent in getting people to feel comfortable with a consensus set of numbers here.
Yeah, like when Sarah does these workshops, for 3 days, it's 2 days about is to do what you just described. You have to get everyone to explicitly state their values and how those values feed back into this. So you could create multiple versions of that utility to reflect the different value systems. Okay, if this is what I care about, then these are my utilities. This is what I care about. And then none of us know. We just But it's, you have to actually formalize what it is you care about. Some can be done in consensus. And others no. The other funny thing is that there was like, all these people sit down, and we're all sure none of us agree on anything. And then over the course of a couple of days, you realize that actually most of us care about the exact same. So that, yeah, it's the social side of this is huge. I don't think this is.
Okay. Oh, yeah, Marika. Yeah. Yeah, no, I think you're exactly right. The need for a forecast in Idaho is a little different than Oregon and Washington, where they don't have real-time assessment of what's going on. So it's a little bit of the in-season versus pre-season need for forecasts, as well as, you know, how much flexibility do you even really have to change the harvest? And it's a complex thing to begin with. And, you know, in Oregon, we would set out plans that have 10-year lifespans. And so this sort of analysis would happen once. And then we just go for 10 years. And then we sit back, come back to reassess whether we need to change it. So we're kind of a slow turning ship. Well, we only have a few more minutes. What I wanted, this is Netica software. In the slides, there's a link to where you can download this. And what I really want to point out here is that you don't have to know Bayes' theorem and that what I had on the slide. If you know instead how to just kind of draw some boxes and put some arrows between them, you can have it do the computation for you. And including the whole piece about multiplying the probability of states of nature into our utility that we reap from it, all that can happen in here as well. And if I had more time, I would show you how to set up one of these models, because I could probably in 10 minutes, I could show you how to do this and it'd be like, wow, that's cool. Because you don't have to know any of the Bayes math. But the thing I guess to point out is that here I've got one working. I know it's super small. Let me see if I can zoom in. Zoom. Yeah, there we go. So this is parameterized with the same numbers that were in the table in the slide. So I said if abundance is, the forecast came in high, so I'm going to click on this box high, and it'll collapse the forecast probability down to a point. And we're going to say it's 100% likely that our forecast is high, because you're going to have a forecast. It's going to be some number, and it's either high, medium, or low. So here we're going to collapse uncertainty down to it being high. Now it revised our belief in the different states of nature. And so the true abundance, it's now saying there's a 10.3% chance of it being low. This is, I showed you how to calculate that with arithmetic. But here we're also automatically getting the medium and high states as well. So not too surprisingly, if our forecast is high, we have, you know, our forecast is generally correct. So we have more belief in it being high than any of the other two states. So this is intuitive, perhaps. Buried in this little node here, utility, is that table that I had showed you of the utility that we reap from different combinations of abundances and then different decisions. And then what pops back out, I know it's kind of weird because the arrows go over there, but what pops back out, this is actually the utility we reap from different harvests regimes. If we're going to implement a harvest regime for corresponding to low, medium, or high, and what we see is that we get most utility from a medium harvest, even though our forecast, we were predicting high, and we generally thought that it was going to be high. High was still more likely than the other states. However, because we're risk adverse, and there is a chance that we could actually have a low abundance, it's only 10.3% chance, but because there's a probability of it actually being low, and we are really risk adverse to implementing a high harvest when it's actually low, the decision in this case comes out to implementing a medium harvest regime. And that's just baking in all of these probabilities of the states of nature in light of our known forecast uncertainty and our utilities of getting it right and getting it wrong in the two different ways. Cool, right? I think that's really neat.
You select the medium or low.
Yeah. So medium right there. Yeah, so this one, yeah, corresponds with low. And I think the medium corresponds with medium. Yeah. So it's really only the high because there was so much risk aversion to over harvest that was baked in there. But this is obviously just made up. I just cooked this up. No one is actually doing this. Yeah. Yeah, we're out of time. It's noon. So thank you, Mark. And Sean, we'll let Sean have the last word here. I know he's got a few more announcements, but I think I can speak for Mark in restating that we're happy to chat more about anything you saw today, and looking forward to seeing you and having those conversations.
Thanks very much. Well, I really appreciate the great work kicking this off. This is actually going to be the first of several different activities related to forecasting over the conference, and I'll just highlight a couple of them. Online today, we've had folks from the Salmon Ocean Ecology meeting, which is taking place simultaneously, and we're going to reverse the flow on Wednesday, where there's going to be 4 presentations talking about these things. We'll start off with Brian Burke at 1 p.m. on Wednesday. And this will be in the pavilion room, and so there'll be a screen introducing a novel stock specific indicator of salmon survival in the marine environment. Then we'll have Elizabeth Daly, winter ichthyoplankton community composition and predicting Columbia River spring Chinook salmon adult returns for 2024. And then Yi Shu, assessing the impacts of environmental and ecological variables on the performance of Fraser sockeye. And then Matthew Bogart at 2 p.m., incorporating marine climate indicators to predict chum salmon, Oncorhynchus heta returns in South Puget Sound, Washington. So you get to see some of the applications of these methodologies. A couple of other things too. Neela Kendall's running a great two blocks for a symposium on escapement methods happening Wednesday afternoon. And then on Thursday, let me see if I can find it. Thursday at 8 a.m. for those eager beavers, we're going to be talking about the Salmon Prize and Sockeye International. So the page that I passed out to everyone, we're going to be talking a little bit about that. We're going to be announcing the winners from our first iteration, and also taking any Q&A from anyone that's interested in this. So yeah, I'd just like to, again, thanks Matt and Mark. Brilliant overview, and I look forward to hearing from everyone.